Today we're going to start off with adding a couple postulates and theorems to your Chapter 3 postulate paper. So start on that document first. Theorem 3.8 says that if two lines are parallel to the same line, then those two lines are parallel to each other. In other words, if A is parallel to B and B is parallel to C, then A is parallel to C. Logically, this makes sense. If A is parallel to B, but B is also parallel to C, then you can conclude that A and C have to be parallel to each other as well, because they are parallel to the same line. Make sure you copy down that conclusion as well as the diagram. Theorem 3.9. In a plane, if two lines are perpendicular to the same line, then those two lines have to be parallel to each other. In other words, if A is perpendicular to C and B is perpendicular to C, then A and B have to be parallel. Remember that perpendicular, which is what the symbol stands for. If you see this upside down T, that stands for the word perpendicular. Perpendicular really just means where two lines intersect, they create a right angle. So if A is making a right angle with C and B is also making a right angle with C, A and B have to be parallel lines. In terms of everyday logic, this makes sense. Picture yourself driving down road A. If you make a right angle turn onto road C, and then you make a second right angle turn on road B, you would say that you are on the street parallel to A. In other words, two right angle turns gets you on a parallel line. Go ahead and copy down the conclusion as well. A is parallel to B. Last theorem for the day coming up. Perpendicular transversal theorem. This theorem says that in a plane, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. In other words, if A and B are parallel, and line A is perpendicular to line C, then B has to be perpendicular to line C as well. Picture it like this. If A and B are parallel lines here and C is perpendicular to A, it makes sense that B would also have to be perpendicular. So that's your conclusion. After you fill in that box on your postulate paper, now go to your 3-4 notes. Copy down this definition. The word perpendicular is familiar, but reminding yourself of what it means will be especially important when you get to the proofs today. Perpendicular lines are defined as lines that intersect to create right angles, 90-degree angles. Now, when you are writing proofs today, it'll be really helpful for you to fill in this chart summarizing the three theorems you just learned. So Theorem 3.8 says, if you think of it in the summary version, if you highlight the repeating line names, in this case line A is in both of those first two, you could take out the repeats and put together what's left. B is parallel to C. That's Theorem 3.8. Theorem 3.9, you could highlight the repeats, line A, and put together what's left, but if you have two perpendiculars, two right turns, it gets you on a parallel line. So B is parallel to C. Put together the line names left, B and C, and put a parallel between them. The perpendicular transversal theorem, when you're writing proofs, it's okay to abbreviate the word perpendicular with your perpendicular symbol. Your perpendicular transversal theorem says that you could highlight the repeats, line A, take them out so you're left with B and C, and one parallel and one perpendicular symbol gets you a perpendicular. Now, one more thing you might want to add to that chart is a little bit of a shortcut that might help you memorize these three rules about what combination of parallel and perpendicular results in a parallel or a perpendicular result. Write this down. Memory trick. If you think back to your multiplication rules with signs, like positive times positive gets you positive and so on, negative times negative gets you positive, think about those rules and then match the word parallel with positive and the word perpendicular with negative. So this is actually a good technique to use in general with math when you're learning new laws or rules of math. Compare them with the rules you already know and see if there's a similar pattern to make memorization easier. For example, you know how a positive times a positive gets you a positive answer? That's kind of like how two parallels get you a parallel. And do you know how a negative number times a negative number, the negatives cancel out and gets you a positive answer? Two perpendiculars cancel out and get you a parallel answer. Now, you know how with multiplication, if you have one of each, one negative times one positive, it's a negative that wins? That's a little bit like your last theorem. If you have one of each, one parallel and one perpendicular, the perpendicular wins. So if that technique helps you memorize the rules, it might be useful, but it's just a memory technique. There's not actually a connection between positive numbers and parallel or negative numbers and perpendicular. It's just a remarkably similar pattern. For each combination of relationships, tell how X and Z relate. Justify your answer. A tip on these is to highlight the line names that repeat. And then look at your summary of the three theorems from today. If you have two perpendiculars, what does that get you? If you put together the line names left and you say two perpendiculars get you a parallel, well done. Which theorem was that? Theorem 3.9 says two perpendiculars get you a parallel. Two right turns get you on a parallel street. Try question 2. For question 2, you can highlight the repeating line names. Look at your summary of the theorems. One perpendicular and one parallel gets you a perpendicular. And put together the names of the lines left. That would be perpendicular transversal theorem. Next, we're going to try the same type of question, but we'll make it a little bit more complicated because now we have more lines in the same scenario. So for question 3, just look at the first two sections of the problem and highlight the repeats. Put together what's left and figure out whether it will be parallel or perpendicular. One parallel, one perpendicular gets you a perpendicular. So A is perpendicular to C. Then look at that last section. The last fact you know that you haven't used yet is that C is parallel to D. Compare that with what you've already figured out and highlight the repeats there. Oh, and just a tip. Don't forget to justify your answer. Write which theorem you used. We used perpendicular transversal theorem to say A is perpendicular to C. And then some people like to bring down the last fact from the intro that we haven't used because sometimes then it's easier to identify what's being repeated. And then you could put that together. One perpendicular, one parallel gets you a perpendicular. So A is perpendicular to D, and that would be a second use of the perpendicular transversal theorem. Remember, to justify your answer means to write the theorems you used to make your conclusion. So remember to do that with question 4. Highlight in the first two sections the repeating line names. What conclusion can you make from those first two statements? What theorem did you use for that? Two perpendiculars make a parallel is theorem 3.9. You may find it helpful to bring down the one fact you haven't used yet and highlight the repeats. And you can use perpendicular transversal theorem again to say A is perpendicular to D. So that's going to be one of the techniques you use the most on the proofs you write today. Go ahead and make your statements and reasons T-chart for your proof. So our goal here is to prove Theorem 3.9. Theorem 3.9, the summary version said, if A is perpendicular to B and line B is perpendicular to C, then lines A and C are parallel to each other. To prove that, remember that when you're proving a theorem, which is usually written as a conditional sentence, the if part, the hypothesis, is actually your given, and the then part, the conclusion, is actually your end goal, what you're trying to prove. So when you're filling in step 1, the given, it's just going to be what's after the if. Now, the thing about proving theorems is that you are not allowed to use circular logic. You cannot use Theorem 3.9 to prove itself. But any previously learned theorems besides that are free to use. All right, so we can't use Theorem 3.9, the rule that says if you have two perpendiculars, you could highlight the repeats and put together what's left. But what else can we figure out based on the fact that we have two sets of perpendicular lines? Well, if you look back at the definition of perpendicular you wrote on your notes, perpendicular tells us that where A and B intersect, there's a right angle, and where B and C intersect, there's a right angle. Because perpendicular just means where two lines intersect, it creates a right angle, or a 90-degree angle. So add right angles to your diagram, and then write the fact that angles 1 and 2 are right angles for step 2. Now, to figure out that we had these two right angles, we really just used the fact that the intro had the symbol for perpendicular. In other words, the word perpendicular told us we had right angles. Definition of perpendicular is your reason for step 2. And it's okay to use the symbol for perpendicular as shorthand, or you could write out the word perpendicular if that works better for you. Either way is good. Now, if angle 1 and angle 2 are right angles, that means they are equal sizes. They are congruent angles. If they're both 90 degrees, they are congruent to each other. The reason you could say angle 1 is congruent to angle 2 is really pretty fascinating. Look at your old chapter 2 postulate paper. On there, there's a theorem that says that if two angles are both right angles, then they're congruent angles to each other. And it's called Theorem 2-4. Theorem 2-4 is actually surprisingly useful for proofwriting when you're talking about right angles, even though it's stating kind of an obvious fact. If you have two angles that are both 90 degrees, they have to be equal to each other. Now, you're actually almost done with the proof. There's only one more step. We are almost to the point where we could prove that A is parallel to C, because if you look at angles 1 and 2, there's a name for that sort of angle pair. What is that angle pair called? If you said corresponding angles, well done. Now think back to earlier in chapter 3. On your chapter 3 postulate paper, you have a list of theorems you can use to prove lines parallel, which is our goal here, to prove A is parallel to C. Find the one you could use here. If you said converse of corresponding angles theorem, well done. The idea is, because we have corresponding angles that we just said had to be congruent to each other, we could use converse of corresponding angles theorem to say we have parallel lines. And that is your official proof for Theorem 3.9. Now we're going to try some proofs using today's new theorems. Go ahead and make your statements and reasons T-chart and fill in step 1. Now, to figure out step 2, think back to what you did at the beginning of today's notes. How can you combine the facts that A is parallel to C and B is parallel to C as well into a new conclusion? If you highlighted the repeats and put together what's left, well done. Which of today's theorems lets you do that? Theorem 3.8. If two parallels are together, it gets you a new parallel fact. Now here's the deal. Now that we know that A and B are parallel lines, we know something about angles 1 and 2, the two angles between A and B. We know that angles 1 and 2, because they're between parallel lines, have to be congruent to each other. Because they're between parallel lines and because the type of angle pair they are. What's the name for that sort of angle pair? They're alternate interior angles. They are opposite sides of the transversal and anterior the parallel lines A and B. Alternate interior angles theorem justifies saying that they have to be congruent to each other. So now that we know that the measures of angle 1 and 2 are equal, we're almost done with the proof because our end goal is to just say that the measure of angle 1 is really 65 degrees. And we already know that angle 2 is 65 degrees. If we just said they're equal, now we could just say, well, where measure of angle 2 was in step 3, I can plug in the value I know measure of angle 2 equals 65. What property lets you plug in and replace things? You could say either substitution property or transitive property here. Sometimes they can be used for the same purpose. Well done. Try the next proof. Go ahead and create your statements and reasons T-chart. And fill in step 1. If you just look at the first two facts from your given, how can you combine them? If you highlighted the repeats and realized how you could put together what's left, well done. What reason did you use? Theorem 3.8 to say two parallels get you a new parallel fact. Now you can take your new conclusion from step 2 and compare it with the last fact from the given you haven't used. Is there a repeat that you can highlight, and how can you put together what's left? One perpendicular and one parallel gets you a perpendicular fact. So A is perpendicular to D. That matches the proof, so you just need to justify it with a reason and you're done. Excellent work. Try the last one. Look at just the first two facts and figure out how you can combine them to make a new conclusion. What reason did you use? Excellent work. Now look at your current conclusion and your third fact, B is perpendicular to line Q. What conclusion can you make from that? And what reason would you use? Excellent work. Now look at your last fact from the given that you haven't used yet. Compare it with your step 3. Two perpendiculars make a parallel. And that's theorem 3.9.